All right, so here's session 8.5, the integration by partial fractions. So in these sessions, we will focus on the integrating rational function. So that's polynomial over polynomial, okay? So pretty easy to recognize. Now, before we get to the new technique, let's review the simple integration first. So let's do it when we integrate 3 over x minus 3 plus 2 over x plus 1. You see this function, it's a sum of two rational functions, but each of these is actually easy. If you recall what we have from, I think, 8.1. So we have what's techniques here, the u prime over u. So by now you should know the formula, the integrations of u prime over u. It's natural log of absolute of u plus constant. All right. So if you look at this, what is the derivative of x minus 3? Well, the x minus 3 is 1, right? So technically that you need to form, you need the ones at the top. So when you rewrite, you could integral of something like 3 times 1 over x minus 3 plus, and then same thing with the derivative of x plus 1, it's 1. So you put, I'll write that as 2 times 1. I don't think we need that step in the future, but just trying to make it clear so you can see. So this one and that one both follow the form u prime over u. Okay, and therefore when you integrate, then that one is 3 times natural log of absolute of x minus 3 plus 2 times the natural log of absolute of x plus 1 plus c. Okay, so you see it's pretty quick for that one. Use natural log to natural log u prime over u. Right? Now let's look at number 2. In number 2, we have several functions. Again, it's just a sum and differences of functions. So it's not that hard, right? I can integrate term by term. Now each of these, we have a slightly different techniques here. So if you observe again, when you have a regular function, this has degree 1, degree 2. So it looks like it might fit the form u prime over u. Again, that is what this is. U x squared plus 1. What's the derivative of x squared plus 1? It's 2x. Match the form. So that one I can do immediately. That is the u prime. That is the u. Okay, so I can integrate. Then we come to the next term. See, what is that? If you look at carefully, we have direct formula. That's 1 over 1 plus x squared. That is the arctangent. The arctangent, you know, and review that formula there. So we have the formula. And then you look at the next one. Well, the next one actually is similar to one of these two up here, right? It's actually u prime over u, right? So if this is the u, then the derivative of u is 1. So basically I do have it there. Okay, u prime over u. I can use the formula. And then the last one, for the last one, you got to do, well, that's different, right? If you take a derivative of this, it's 2 times x minus 1, so it doesn't fit u prime over u. You got to use power rule in this case by rewriting. So that one we can rewrite as x minus 1 to the, instead of plus 2 to the power positive 2, it's going to become a negative 2 power, right? So it's reciprocal, right? So from here, now I can integrate term by term. The first one is u prime over u, so it's a natural log absolute of x squared plus 1 plus, that is the arc tangents of x. The third term, well, the same thing, it's a natural log 2 times the natural log of x minus 1. And the last term, use the power rule, you add 1 to exponents, and that is x minus 1 to the negative 2 powers over, if I add 1 to it, right? So I add 1 to the exponent, so that's to the negative 1. Divide the new exponent, negative 1. You may simplify that, but anyway, so that's the answer, right? So that's a quick review of the integrations where you might use different formula, but that's, again, it's just easy. Now, what makes it hard is when you have rational function is more complicated than this. Degree 2, degree 3, degree 3, degree 4. So you might have a whole bunch of integrals that you have to, a whole bunch of fractions that you have to deal with, like this one. Okay, let's look at the first example. If you have 5x minus 3 over x squared minus 2x minus 3, right? That one. Now, if you're trying to follow the form u prime over u, look at the denominator here. What's the derivative of x squared minus 2x minus 3? It's 2x minus 2, and I have 5x minus 3. So it is a match, okay? So we cannot use the form. So the one way to do is, if we wish, the integral, the fraction is that simple, right? Instead of this. So what we're going to do is we're going to rewrite these fractions as two separate terms, right? So separate terms. So rewrite that as the sum of the difference of two terms. Hopefully those are easier, okay? And we can integrate it the same way we did after we separate them. So you will wonder, okay, how do we separate them? Well, think about this. Let's say you have the fractions. I'll make the one that's actually easy, but let's say you have 5, 6, okay? The fraction of 5, 6. And then you're like, oh, 5, 6. Okay. And all right, so let's say this fraction, we feel like still too big, then this one turned out to be 1/3 plus 1/2. Okay, 1/3 plus 1/2. So you see that the fraction here is smaller and smaller, and then we like that. Okay, imagine if you have the fraction that's huge, right? And then you hope to write that the sum of difference of many smaller fractions, where you don't have to deal with the big numbers like we did over here. So instead of doing 5, 6, we're doing 1/3 and half. But the question is, how do we know, like this one, how do we know it's going to be some difference of what fractions, what smaller fraction? How do I know it's 1/3 and a half add up to 5, 6? Well, look at this way. Because when you add them, right, you see the denominator, this is a 3 and 6, the common denominator 3 and 2 is 6. So if you go backward, if you were to separate them, right, make them smaller, then you might want to look at the denominators and the factor of 6. In this case, 3 times 2. That's kind of give us a clue that the new small denominator would look like. Okay, so that's how we do. So if give me 5, 6, look at that 6 is 3 times 2, then I'm thinking it might be something over 3 plus something over 2. And this unknown on the top, of course, I need to figure it out. We can label A and B the unknown and try to figure out what the numerator will equal, will add up to 5, 6. Now, this is essentially what we will be doing here, although we'll be dealing with a rational function, but the same way. And so that's why you see the first step, what I would do is look at the fractions I have, look at the factor form, like 6 split into 3 times 2. And then here, I do the same. I want to split into x minus 3 and x plus 1. Don't forget that we do this by factoring this trinomial. Okay, so I hope you remember how. So x and x, then two constant multiply -3, added to -2. So we factor the denominator first. After we do, then I know, all right, so that must be something over the smaller denominator, and then something over the second smaller denominators, where you're trying to figure out what will add up to this. See, analogy here, similar to the fractions, we'll do numbers. Okay, so now what we're gonna do is, okay, x minus 3, x plus 1. Since the numerators I don't know the answer yet, I put the capital A, capital B as unknowns, constants. And then try to figure out A and B. All right, so from here, if you want to figure out A and B, since this is equal size, so we can treat that as an equation, multiply both sides by the LCD. Right, LCD. Right, so what's LCD? Well, it's going to be x minus 3 times x plus 1. So if you multiply both sides by the common denominators, which is this, right? So if you imagine you time x minus 3 and x plus 1 on the left, and then you take x minus 3 times x plus 1 on the right. When you multiply on the right, you actually distribute it in. You see this one and that one cancel. If you multiply it in the first fraction, there's an x minus 3 cancel. You're left with a times x plus 1. Okay, but then when you multiply the second term, the x plus 1 got canceled, and you're left with b times x minus 3. Okay, so when you multiply it in, you will get this. Okay, so numerators, denominators on the left gone. You have a times x plus 1 plus b times x minus 3. Okay, now from here, you can multiply both sides by, I can distribute the a here, distribute b there. So you have ax plus a plus bx minus 3b. Okay. Right, so multiply it out. Now from here, you may wonder how we're going to solve these equations. Don't forget that this is, again, equations. The left-hand side equal the right-hand side. Now, on the left side, I have 5x. On the right-hand side, what do I have? I have an x term, ax. I have a bx term. Now, these are the x terms. If the left-hand side equals the right-hand side, these two combined has to be 5, right? Has to be 5. Then you have a constant term, 3, -3 on the left. You have 2 constant terms on the right. These 2 constant terms on the right has to add up to -3, or else they won't equal, right? Okay, so what it means is you can equate the coefficients. Okay, we could say set like term equal to each other's. The 5x has to be ax plus bx. The -3 has to be a minus b times 3. And from here you can see we have two equations technically to solve. Right? We have two equations. So if we get rid of the x, it will mean phi has to be a plus b. And we also have that is negative 3 times b. Okay. Now I have two equations and two unknowns here. So can we solve that? Yes. We have several techniques: addition method, we have substitution method, we have matrices if you know matrix, the method. But he want to use addition method here. Okay. So I think it's not too hard though. You see phi equal a plus b, right? If I want to eliminate, let's say, the constant a, all I do is I multiply these second equations by negative 1. Negative 1, negative 1, negative 1. That would change the sign. And you see a, negative a. So then I'm going to add the two equations. Left hand side, 5 plus 3 is 8. The right hand side, you see how the denominator, the a got cancelled. Yeah, b plus 3b is 4b. From there, of course, b got to be 2. Once it got b to be 2, using the first equation here, plug in phi equal a plus 2. That means a is 3. Okay. Now when a is 3, you see that initially our fractions is this one, right? We integrate this, but then this equal, we've just found a is 3, b is 2. So they're the same. Instead of integrating this fraction, I integrate the partial smaller fractions. Okay. Now these two I can do, not the problem, right? This is again u problem of u. And look back to the example we did earlier. It's really the very first one we did here. See that one? Okay, so we already did. So it's the same problem, but after we separate them, you see that's that, and that is the answer. Okay, 3 natural log x minus 3 plus 2 natural log x plus 1. And this technique is called partial fractions or partial fractions decomposition. Okay, so you can see from this example, the key is how we're going to separate them, right? From A, separate into sum of two small fractions. And so we need to know the form and how to do that. From there, the integration is actually it's simple. Now, before we move on to the strategy in general and other examples, I'm going to give you another way to solve A and B. Sometimes it's shorter, sometimes longer, but most of the time we prefer the second method. It's better. Now, if we look back to, here's an example we have, right? We multiply both sides. The shortcut here I'm going to show you it's called Heaviside method. It's named after the English engineer, Oliver Heaviside. Now, when we multiply by the common denominator, that's what we got, right? So the first method that we did is we multiplied out and equate the like terms. Now the second method relies on the fact that the polynomials on the left and right equals, of course, it can equal for every values of x, regardless of what x is. So that means no matter what x you put in, you always have this equality. So by understanding this idea of every values of x could be plugging, and they still equal, we can pick some nice values of x that we plug in to give us an edge. An edge in here could help eliminate variables that we need to solve. For example, you see, look at these b times x minus 3. The number that I think of is 3 here, right? If x is 3, then you have a 0 times b, so the b will be gone, so you can solve a easily. And if you don't want the a to be present, I'm thinking x might be -1, right? Plus 1 is 0, then a will be gone. Okay, so what I'm gonna do is, let's say I choose x to be -1 and plug in. Don't forget that -1 will go into every x. Okay, if you plug -1 in, you have -1 times 5 minus 3. And -1 minus 3 here, it will be -4. Okay, so you got a -80. That is 0, a, and then -4 will be times -4. And well, that's 0. -8 is b times -4, so you see that b has to be 2. And then do it again with the different values of x. How about 3? When you plug 3 in, 3 minus 3, you see that's 0. That's 0b. And 3 plus 1 got 4. And then don't forget the left hand side. 3 times 5 is 15 minus 3 got 12. So that's gone. And then you have 12 equal 8 times 4. What is a? 3. You see we got the same values. A is 3, b is 2. It's just a different method. They call it Heaviside method. Right? So it's up to you which way you want to go. Okay. Now, let's get to the general idea. Method of partial fractions. When you're dealing with the fractions or the rational functions, make sure that the fraction is proper, okay? Proper fractions. So, in other words, if we encounter a fraction that is improper, what do I mean improper? The numerators has to be, now for the numerical fractions, what we have is a improper fraction is when we have a numerators is equal or greater than the denominator. But when we're dealing with the rational functions or fractions, then it's improper if the degree of the numerator is equal or greater than denominator. So this is improper fractions. Or you have something like that over this. That is improper, degree 4 over degree 3. So when you have improper fractions, what we want to do is we can simplify, like how it's simplified. If you 7 and 6, it's just the same as 1 and 1/6, right? 5 over 5 is of course just 1. So likewise, when you have degree top, degree bigger than degree bottom, so equal to degree bottom, you have improper fractions, and then to do that, you're going to use long divisions, the same way we got 1 and 1/6. How do we get that? Actually, do the long divisions here, 7 divided by 6. I think you got 1 time and then the remainder of 1. Okay, so it's really long divisions. And we're going to do the long divisions, But of course, here with the long divisions of polynomial, you need to review that as well. If you don't remember, we're going to use long division to write as a sum of a polynomial in a proper fraction. Okay, we'll illustrate with an example later. Now in step 2, let's say the fraction is proper. Then we're going to do by partial fractions, first by factoring the denominator completely. So be sure to factor the denominator out completely. So completely means when you have x cubed minus x squared, x squared cubed minus just x cubed minus x, let's say that's in your denominator, right? If you factor out the x, then you have x squared minus 1, but then you don't stop there because it's not completely factored. Then we have the difference of square here. That's the same as x times x minus 1 times x plus 1. So you see I have 1, 2, and 3 factored at the bottom. 3 factored at the bottom. Okay. So that's when I completely factor it. You cannot factor this further. Okay. Now, once you have the factor form of denominators, then you look at the denominator and determine how many fractions we're going to be split or decompose. Like in this case, you have 3 x minus 1, x plus 1. So your denominator will have, your partial fraction here must have 3 denominator. X minus 1 and x plus 1. Now notice that in this case, we have 3 factors. Each of these we call linear factor. You see there's no power, linear factors. Then when you have linear factors, the numerators we're going to have to be a constant. So let's say the unknown a's, the unknown b's, unknown c. Okay. So the first thing is when for each linear factor of the form ax plus b to the n, then the decomposition must have the form one. Now here is a bit more complicated than what I've just wrote down. It's just because the linear factors I have written down is only with the degree 1s outside for each of them. Okay, for each of them. Now, if you have something more than just 1, right? So let's say you have so let me look up something. So let's say if your denominators now, I can read. Let's do a completely different example. Let's say your denominators is x minus 1 cubed times 2x plus 3 squared. Like that. Then notice that I have 2 distinct factors, the x minus 1 and the 2x plus 3. Both of these are linear factors because of ax plus b. It's ax plus b. There's no powers there. However, each factor x minus 1 repeated 3 times. X minus 1 times x minus 1 times x minus 1. This is repeated twice, 2x plus 3 times 2x plus 3. Now, this one is saying for each of these factors, if you put the n, then that will be decomposed into as many denominator as the powers. So if you see the 3 there, right? So 3 here. So that means the first fraction will have the form x minus 1 to the first power. The second one will be x minus 1 to the second power. You see how that's go. From 1 to 2 to the third power. Now, here's the third power. So we stop at 3 because that's 3. You're going to repeat the same thing for the factor. I have 2x plus 3 to the second power. So it's going to be 2x plus 3 to the first plus 2x plus 3 to the second. Again, I stop because let's see. So see how the 3 means you have 1, 2, 3. With the 2 there, you have 1, 2. So you're going to total of 5 fractions in this case. Now the numerators will be unknowns. I mean, you can call that A, B, C, D, E. The unknowns, we have 5 unknowns. For the formula here, we use A1, A2, A3, A7. Again, the reason is we may have a lot of them. So we don't like letters. We run out of letters, right? So A, B, C, D, E, F, G, H. So label A1, A2, A3, Z. So these are the unknown you need to find. Okay. Now, if you look at the second form, the second form here is we call the irreducible quadratic factor. So for that one, for each irreducible quadratic factor, then the decompositions must have the form. You see what happened is they look the same, increasing powers the same. Exceptions, with the exception that the numerators now it's going to be a linear factor, okay, instead of just a constant. Now, when I say irreducible quadratic factors, I mean you have quadratic factor but cannot be factored further. Okay, cannot be factored further. For example, when you have something like 4x minus 2, 4x minus. All right, so you see, if I have 3x over x squared minus x plus 3 squared, right? So that one we have quadratic here. You see, x squared minus x plus 3. Now that one you cannot factor further. So that's why we call the irreduced quadratic factor. And since this has the second power, we will have 2 denominators. To start out with, again, this irreducible factor, x squared minus x plus 3 to the first, and then plus the same thing, x squared minus x plus 3 to the second, and stop at the second factor. Now in this case, be aware that on the numerators, there's unknown, but it's not unknown constant in this case. It'll be the unknown linear factor. So that means you're going to have something like ax plus b, the unknown, and maybe cx plus d. So we have actually 4 unknowns on the numerators to solve, right? So once you know all the form of how to factor, then you can actually go from there, right? So that finished the first sections of the 8.5.